right, find your comfortable place and let the world outside your window fade into a gentle blur. Tonight, we're going to embark on a different kind of exploration. We're not hunting for strange creatures or advanced civilizations. Instead, we're going on a quiet, patient search for something much more fundamental: the possibility of life itself, hidden away in the nooks and crannies of our own solar system. We often think of the beginning of life as a dramatic, singular event, a flash of lightning striking a primordial soup, a spark of divine intervention. But what if it's quieter than that? What if life is less like a lightning strike and more like a patient, slow-growing crystal, forming silently and steadily wherever the conditions are just right? What if our solar system isn't a barren desert with one single miraculous oasis, but more like a vast garden with many different patches of soil, each with the potential to grow something wonderful? To begin this tour of potential gardens, we first need to understand the recipe. What are the basic ingredients that scientists believe are necessary for life, at least life as we know it, to get started? It turns out the recipe is surprisingly simple, consisting of just a few key pillars. And understanding this recipe helps us know where to look, guiding our search to the most promising and sometimes the most unexpected places. The first and most important ingredient on our list is water, specifically liquid water. We hear this all the time. Follow the water is the mantra of astrobiologists. But why? What makes this simple molecule so special? Well, water is what's often called the universal solvent. It has a remarkable ability to dissolve more substances than almost any other liquid. This is crucial. Life is, at its core, a series of incredibly complex chemical reactions. Water acts as the perfect medium, a cosmic soup where the building blocks of life can float around, bump into each other, and interact to form more complex structures. Water also has the wonderful property of being a liquid across a wide range of temperatures, which provides a stable environment for delicate chemistry to occur. And it has another strange and vital quirk. When it freezes, it becomes less dense. Ice floats. This might seem trivial, but it has profound implications for life on Earth. If ice were denser than water, lakes and oceans would freeze from the bottom up in winter, killing everything within them. Instead, a layer of ice forms on top, insulating the liquid water below and allowing life to survive through the cold. For all these reasons, the search for liquid water is our #1 priority. The second pillar in our recipe is a source of energy. All life needs energy to power its metabolism. The most obvious source, of course, is our sun. Here on Earth, photosynthesis is the foundation of almost every food chain, turning sunlight into chemical energy. So, for a long time, we assumed that life could only exist on worlds that were close enough to their star to receive ample sunlight. But our own planet has shown us that this isn't true. In the 1970s, scientists exploring the deep ocean floor made one of the most incredible biological discoveries of all time. They found thriving complex ecosystems clustered around hydrothermal vents, volcanic cracks in the seafloor, spewing out superheated, mineral-rich water. There is no sunlight at all down there. Instead, the life in these communities is powered by a process called chemosynthesis. Microbes derive their energy not from light, but from chemical reactions with the sulfur compounds coming from the vents. This discovery was a complete game changer. It told us that life could exist in total darkness, powered by the chemical energy from a planet's own hot interior. This opened up a whole new category of potential habitats for us to explore.
And there's even another potential source of energy that's particularly important in the outer solar system: tidal energy. This is the heat that can be generated inside a moon as it gets squeezed and stretched by the immense gravity of a giant planet it orbits. Imagine repeatedly bending a paperclip back and forth. It gets warm from the friction. It's the same principle, but on a planetary scale. This constant gravitational flexing can generate enough internal heat to maintain a liquid ocean or power geologic activity, even on a moon that is incredibly far from the sun. So our search for energy is not just a search for sunlight. It's also a search for worlds that are geologically or tidally active. The third and final pillar in our recipe for life is the presence of the right chemical building blocks. Life as we know it is carbon-based. Carbon is a wonderfully versatile element. It can form long, complex chains and rings, creating the stable backbone for all the intricate molecules of life, like DNA and proteins. The other key ingredients are often remembered by the acronym CHNOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Now, you might think that these organic molecules are rare and special, a unique property of Earth. But one of the most exciting discoveries in modern astronomy is that they are surprisingly, almost shockingly common. We have found complex organic molecules inside meteorites that have fallen to Earth. We see their chemical signatures in the vast cold clouds of gas and dust that float between the stars. We see them in the hazy atmospheres of distant moons. The basic building blocks of life appear to be scattered throughout the cosmos like seeds on the wind. The universe, it seems, comes pre-stocked with the necessary chemistry.
So, with our simple recipe in hand, liquid water, a source of energy, and the right organic ingredients, we can start our tour. For a long time, the search for life was guided by a simple concept called the habitable zone, which you might know as the Goldilocks zone. This is the region around a star where the temperature is not too hot and not too cold for liquid water to exist on a planet's surface. In our solar system, Earth sits comfortably in the middle of this zone. Venus is on the hot edge, and Mars is on the cold edge. For decades, this was where we focused our attention. But the discoveries of chemosynthesis and tidally heated oceans have completely revolutionized this idea. We now understand that a world doesn't have to be in the Goldilocks zone to have liquid water. The true habitable zones of our solar system might not be on the sunny surfaces of planets, but in the dark, hidden depths of worlds we once dismissed as frozen and dead. The most exciting potential gardens in our solar system might be located far from the sun, in places we are only just beginning to explore. With that in mind, let's begin our journey. And our first stop is a world that sits right on the edge of that traditional habitable zone, a place that was once warm and wet,
but is now a cold, rusty ghost of its former self. We are heading to Mars. When we look at Mars today, we see a cold, dry, desert world. It's a beautiful but seemingly sterile landscape. But if we could travel back in time, say 3 or 4 billion years ago, we would see a very different planet. The evidence is now overwhelming that ancient Mars was a much more habitable place. It had a much thicker, warmer atmosphere. Imagine a Martian sky that wasn't a thin, pale pink, but a thicker, richer blue. Perhaps not as deep as Earth's, but a proper sky nonetheless. With a thicker atmosphere and warmer temperatures, liquid water was stable on the surface, and there was a lot of it. Our robotic explorers have sent back stunning, undeniable evidence. We've seen images of vast, dried-up river channels, some of which are wider than the Amazon. We've seen gracefully curving deltas where those rivers once flowed into vast, still lakes. Orbiters have mapped out what appear to be the ancient shorelines of enormous oceans, particularly in the northern lowlands of the planet. For a period of time, perhaps lasting for hundreds of millions of years, ancient Mars was a true water world. It had all the ingredients from our recipe. It had abundant liquid water on its surface, it had energy from the sun just like Earth, and it had all the necessary chemical building blocks delivered by asteroids and comets. It was, for a time, a second blue marble right next door, another habitable world in our solar system. The question that haunts astrobiologists is, during that warm and wet window of opportunity, did life ever get started? If it did, its time in the sun was limited. Mars was destined for a slow, quiet death as a habitable world. And the reason for its tragic decline lies deep within its core. A planet's magnetic field is generated by the churning of a molten metal core, a process called a dynamo. For reasons we don't fully understand, perhaps because of its smaller size, the dynamo in Mars's core shut down about 4 billion years ago. The planet lost its protective global magnetic field. And without that magnetic shield, the sun's solar wind, a constant stream of charged particles, was able to directly impact the Martian atmosphere.
Over hundreds of millions of years, the solar wind acted like a cosmic sandblaster, slowly but surely stripping Mars of its thick atmosphere, molecule by molecule. As the atmosphere thinned, the pressure dropped, and as the pressure dropped, the liquid water on the surface was no longer stable. It began to rapidly evaporate into the thinning air, where it was then broken apart by solar radiation and lost to space. The water that didn't escape froze, becoming the vast polar ice caps and the extensive underground ice deposits that we see today. The planet grew colder and colder, and its surface turned into the frigid, rusty desert we know. The window for surface life on Mars had closed. This is why our modern exploration of Mars is best thought of as a form of cosmic archaeology. We are sifting through the ruins of a once habitable world, looking for clues of the life that might have been. This is the primary mission of NASA's incredible rovers, like Curiosity and Perseverance. They are robotic field geologists, and they were sent to the places that would have been the most likely to preserve evidence of past life. The Curiosity rover has been exploring Gale Crater, which we know was once a massive, long-lived lake. It has drilled into ancient mudstones, rocks formed from the fine sediment at the bottom of the lake, and has found definitive evidence of not just water, but all the necessary chemical ingredients for life, as well as a stable, long-lasting watery environment. The Perseverance rover is currently exploring Jezero crater, which was once a beautiful river delta. A delta is a perfect place to look for signs of life, as the river would have carried and deposited organic material from a vast watershed into the fine-grained sediments of the lake.
What are these rovers looking for exactly? They're not looking for fossilized bones or seashells. If life ever existed on Mars, it was almost certainly just simple, single-celled microbial life. So the rovers are searching for what are called biosignatures. These are subtle and often ambiguous clues that life might have left behind in the ancient rocks. A biosignature could be a specific type of complex organic molecule that is typically produced by living organisms. Or it could be a strange ratio of different isotopes or versions of carbon atoms, as life often prefers to use the lighter isotopes. It could even be a microscopic texture in the rock, tiny filaments or layered structures called stromatolites, which on Earth are formed by colonies of microbes. Finding any one of these would be an incredible but not definitive discovery. The Perseverance rover is doing something very special. It is collecting the most promising rock samples, sealing them in tubes, and leaving them on the surface for a future mission to collect and bring back to Earth. The only way we can be truly sure if life ever existed on Mars is to study those rocks here in our most advanced laboratories on Earth. But what about the possibility of life on Mars today? While the surface is almost certainly sterile due to the cold, the dryness, and the intense radiation, the story might be different underground. As the surface of Mars died, it's possible that any microbial life that existed retreated into the subsurface. Deep beneath the Martian ground, it would be shielded from the harsh radiation. There could still be pockets of liquid water, or at least salty brines kept liquid by geothermal heat from the planet's interior. This life, if it exists, would be a form of chemosynthesis, deriving its energy from chemical reactions with the surrounding rocks, just like the microbes at Earth's deep-sea vents. It's a tantalizing possibility. A shadow biosphere surviving deep in the Martian underground. So, Mars remains a world of profound questions, a place that had all the right ingredients but may have lost its chance. It is a quiet lesson in how precious and perhaps how fragile a habitable world can be. Let's leave the rusty deserts of Mars behind us now and continue our journey outwards into the realm of the giant planets. Here, in the cold, distant suburbs of the solar system, the traditional idea of a habitable zone completely breaks down. The sun is just a small, bright star in the sky, providing very little warmth. The planets themselves are gas giants with no solid surface to stand on. For a long time, this region was considered a lifeless wasteland. But we were looking in the wrong place. The most exciting potential habitats in the outer solar system aren't the giant planets themselves, but their incredible, diverse families of moons. And it's here, orbiting these giants, that we find the most compelling evidence for hidden, habitable worlds in our solar system today.
The secret ingredient that makes these frozen moons so promising is the immense gravity of their parent planets, which provides a constant source of energy. Our first stop is the court of the king, Jupiter, and its incredible moon, Europa. From the outside, Europa looks like a giant white billiard ball, etched with long reddish-brown cracks. It is a world covered in a thick, global shell of water ice, estimated to be anywhere from 10 to 30 kilometers thick. The surface is one of the coldest places in the solar system, but beneath that cold, hard shell lies Europa's great secret. The moon is constantly being squeezed and stretched by Jupiter's colossal gravity and by the gravitational pull of the other large Galilean moons. This process, which we call tidal flexing, generates an enormous amount of friction and heat deep within Europa's interior. And scientists are now confident that this tidal heat is enough to maintain a vast global ocean of liquid salt water beneath the icy crust.
This isn't just a small, trapped layer of water. Scientists estimate that Europa's hidden ocean could be up to 100 kilometers deep. For comparison, the deepest part of our ocean on Earth, the Mariana Trench, is only about 11 kilometers deep. This means that this small, unassuming moon, which is smaller than our own, could contain more than twice the amount of liquid water as all of Earth's oceans combined. It is the great water reservoir of our solar system, all hidden away beneath a shell of solid ice. The evidence for this ocean is written all over the moon's face. When we look at high-resolution images, we see a surface that is remarkably smooth and young, with very few craters. This tells us that the surface is constantly being renewed or repaved from below, likely by fresh water or slushy ice from the ocean welling up and freezing. The surface is covered in a web of long linear cracks and reddish-brown ridges. Scientists believe these are fractures in the ice shell caused by the constant tidal stress from Jupiter. The reddish material seems to be salts and other minerals that have been churned up from the ocean below and then irradiated by Jupiter's intense radiation belts. Most excitingly, there are vast regions of what is called chaos terrain. These areas look exactly like sea ice on Earth that has broken up into large chunks or rafts, which have then drifted apart and refrozen in new, jumbled positions. It's powerful evidence that the ice shell is not a solid, static block, but is floating on a liquid ocean beneath, allowing for this kind of movement. All the signs point to a vast, dark, global sea, a place of immense possibility.
So we have all the ingredients from our recipe. We have liquid water, and a lot of it. We have energy, not from the sun, but from the constant tidal flexing of Jupiter's gravity. And we almost certainly have the right chemical building blocks, delivered by comets and asteroids over billions of years, and likely leaching from the moon's rocky core into the water. The question then becomes, what might be happening at the bottom of that ocean? On Earth, deep beneath the waves where no sunlight can reach, we have hydrothermal vents. These are cracks in the seafloor where superheated, mineral-rich water from the planet's interior gushes out, creating a kind of underwater hot spring. And these vents are oases of life, They support entire ecosystems of strange and wonderful creatures that thrive in total darkness, powered by chemical energy. It is a very real possibility that Europa's ocean floor is home to similar hydrothermal vents. If so, they would be the perfect environment for life to arise and potentially to thrive. Imagine, deep beneath kilometers of solid ice, in an ocean that has not seen the sun for billions of years, a chain of these warm, chemical-rich vents. It's one of a handful of places in the solar system where life could plausibly exist right now. Of course, getting there to find out is an immense technological challenge. Future missions, like NASA's Europa Clipper, will perform dozens of close flybys to map the ice shell, confirm the ocean's depth and salinity, and even try to sample the faint plumes of water that may be erupting from the surface. An even more ambitious future mission might send a lander, and perhaps one day a cryobot, a robotic probe that would melt its way through the entire ice shell to finally dip its sensors into that hidden alien sea.
For now, Europa's ocean remains a tantalizing mystery, a quiet promise locked away beneath the world of ice. Let's leave this fascinating moon and continue our journey outwards to the next great gas giant, the ringed planet Saturn. Here, too, we find that the most exciting places are not the planet itself, but its moons. And one of them, a tiny moon called Enceladus, has turned out to be one of the most spectacular and promising objects in the entire solar system. Enceladus is small, only about 500 kilometers in diameter. You could fit it comfortably between Los Angeles and San Francisco. From a distance, it looks like a bright, white, icy snowball. For a long time, scientists thought it was just that, a small, frozen and geologically dead world. But then, in 2005, the Cassini spacecraft flew by and saw something that changed everything. Erupting from a series of long, parallel cracks at the moon's south pole, fissures nicknamed the Tiger Stripes, were gigantic, brilliant plumes of water vapor and ice particles. The little moon was alive. It was spewing the contents of its interior out into space, creating geysers that shot hundreds of kilometers high. This was a bombshell discovery. Like Europa, this tiny moon was being heated by tidal forces from its parent planet, Saturn, enough to maintain a liquid water ocean beneath its icy shell. And the cracks in the ice provided a direct conduit from that hidden ocean to the vacuum of space. But the most incredible part of the story was yet to come. The Cassini spacecraft was able to fly directly through these plumes, using its instruments to taste and analyze what they were made of. It was, in effect, sampling a subsurface ocean from hundreds of kilometers away. And what Cassini found in those plumes was truly astonishing. It found exactly what astrobiologists had been dreaming of. First, it confirmed the plumes were about 98% water vapor with frozen ice crystals mixed in. Second, it detected simple salts, like sodium chloride, table salt. This was a critical clue, as it meant the liquid water was in direct contact with a rocky core at the bottom of the ocean, leaching minerals into the water just like Earth's oceans. A purely water-on-ice ocean would be much less interesting, but a salty ocean in contact with rock is a much more dynamic environment. Then, Cassini found something even more exciting: tiny nanoparticles of silica dust. On Earth, silica dust like this is only formed in one specific environment, when very hot water, over 90 degrees Celsius, interacts with rock. This was the smoking gun for active hydrothermal vents on the seafloor of Enceladus. And finally, to top it all off, the plumes were found to be rich in a variety of organic molecules, including methane, propane, and formaldehyde, as well as molecular hydrogen. So, to recap, this tiny moon has a liquid saltwater ocean, it has active hydrothermal vents on its seafloor, providing a source of chemical energy, and it has all the necessary organic building blocks. It is literally serving up all three pillars of our recipe for life on a silver platter, spraying them out into space for us to find. For this reason, many scientists now consider Enceladus, not Mars or even Europa, to be the single most promising place in our solar system to search for life as we know it. We just need to go back with the right instruments to look for the definitive biosignatures.
Now, let's leave this spectacular little geyser moon behind and drift over to another of Saturn's moons, a much larger and, in many ways, much weirder world. We are heading for Titan. Titan is Saturn's largest moon, and it is a true giant, bigger than the planet Mercury. What makes Titan so unique in the solar system is its atmosphere. It is the only moon to have a thick, substantial atmosphere. And when I say thick, I mean it. Its atmosphere is about 50% denser than Earth's, and it's composed almost entirely of nitrogen, just like ours. But that's where the similarities end. The atmosphere is filled with a thick orange organic smog, a photochemical haze created as sunlight interacts with the methane in its upper atmosphere. This orange smog completely hides the surface from view in visible light. For a long time, we had no idea what lay beneath. Then in 2005, the Huygens probe, which was carried to Saturn by the Cassini spacecraft, made its historic descent. As it parachuted down through the hazy layers, it revealed a landscape that was both alien and shockingly familiar. It sent back images of branching river-like channels carving through highlands, flowing down into what looked like vast dark seas. It saw shorelines and islands. It was a world shaped by liquid. But on Titan, it is far too cold for liquid water. The surface temperature is a steady minus 180 degrees Celsius. At this temperature, water ice is as hard as granite and forms the bedrock of the planet. The liquid that carves the rivers and fills the lakes on Titan is not water, but a mixture of liquid methane and ethane, which behave like gasoline at these frigid temperatures. Titan has a full methane cycle, just like Earth's water cycle. It rains liquid methane from the sky. This methane flows in rivers to the seas, and then it evaporates back into the atmosphere to form clouds again.
So Titan presents us with a fascinating, almost philosophical question. We have a world with a stable liquid on its surface, a thick nitrogen atmosphere for protection, and a surface rich in incredibly complex organic chemistry, with all the building blocks for life raining down from the sky. But the liquid is methane, not water. This leads to the tantalizing possibility of life as we don't know it. Could some strange, exotic form of life have evolved to use liquid methane as a solvent instead of water? The theoretical biochemistry would be completely different. A life form on Titan would likely be what we call a methanogen. It might breathe in hydrogen gas from the atmosphere and eat the organic molecules on the surface, producing methane as a waste product. Its cells couldn't use the familiar lipid bilayers that form our cell membranes, as they would dissolve in liquid methane. Instead, scientists have theorized that they could be made of different molecules, called azotosomes, which would be stable in the methane seas. We have absolutely no idea if such a life form exists, but Titan is a perfect natural laboratory to test the limits of what life can be. But the story of Titan has one more twist. While its surface is a world of methane, scientists believe that deep beneath its icy crust there may be another ocean, this one made of good old-fashioned liquid water, kept liquid by heat from its core and insulated by the thick ice shell. So Titan may, in fact, have two potential abodes for life: a strange, exotic one on its surface, and a more familiar, watery one deep below. It is a world of incredible complexity and possibility. Our tour of the big three most promising locations, Mars, Europa, and Enceladus/Titan, is complete. But the solar system might still hold a few more surprises, a few more potential gardens in some very unexpected places. Let's take a quick, quiet look at some of the intriguing long shots. First, let's travel all the way back to the inner solar system, to the planet we dismissed as a hellscape, Venus. We know the surface of Venus is completely inhospitable, with its crushing pressure and lead-melting temperatures. But what if we look up? High in the Venusian atmosphere, about 50 kilometers above the surface, the conditions are surprisingly Earth-like. At that altitude, the temperature and pressure are similar to what we experience on the ground here on Earth. It is, in a way, the most Earth-like environment in the entire solar system, other than Earth itself. Could life exist not on the surface, but floating in the clouds of Venus? It's a very old idea, but it has gained some new traction recently. The idea is that simple single-celled microbial life could float in the temperate cloud layers, using sunlight for energy and feeding on the chemical compounds in the atmosphere, perhaps living within the protective droplets of sulfuric acid. This idea was bolstered in 2020 by the highly debated announcement of the detection of phosphine gas in the Venusian atmosphere. On Earth, phosphine gas is a smelly, toxic gas that is almost exclusively produced by living, anaerobic organisms.
Its potential presence on Venus is a tantalizing clue, but it is far from definitive proof, and the discovery remains highly controversial. Venus remains an intriguing, if very challenging, place to look.
Now, let's leave the inner solar system behind again and travel out to the main asteroid belt, that vast, mostly empty expanse of rock and rubble between Mars and Jupiter. For a long time, this region was thought to be just a collection of dead, inert rocks, the failed remnants of a planet that never formed. But lurking within it is a world that has completely changed our perspective on where water, and perhaps life, could be found. We are visiting the dwarf planet Ceres. Ceres is the largest object in the asteroid belt, a small, spherical world about 940 kilometers in diameter. For a long time it was just another point of light, but in 2015, NASA's Dawn spacecraft arrived and went into orbit around it, revealing a fascinating and surprisingly active world. The most striking features that Dawn discovered were a series of incredibly bright, almost dazzlingly white spots on the surface, particularly inside a large crater named Okator. These spots looked like lights left on in an empty house, and for a while, their nature was a deep mystery. After careful study, scientists determined that these bright patches are deposits of salt, specifically sodium carbonate. This is a crucial clue. These are not just dry salt flats. They are thought to be the remnants of a briny, muddy liquid from deep within Ceres that has recently welled up to the surface through cracks and fissures. As the water sublimated into the vacuum of space, it left behind these bright, crusty salt deposits. This was the first piece of strong evidence that Ceres isn't just a dead rock, it has a dynamic interior. Further study has shown evidence of cryovolcanism, ice volcanoes, that were active in the very recent geological past.
The conclusion from the Dawn mission is that Ceres likely has a substantial subsurface ocean, or at least a large, mushy layer of brine and rock. It is, in a sense, a fossilized ocean world. It might not have the same powerful energy source as a moon like Europa, which is constantly being flexed by a giant planet, so its ocean may be partially frozen or very, very salty. But the presence of liquid water, organic molecules, which have also been detected on its surface, and salts makes it another intriguing place to consider. It suggests that even in the cold, lonely asteroid belt, small worlds can hold onto hidden reservoirs of the most important ingredient for life. And this leads us to the final, most distant region of our tour, the frigid, dark frontier beyond Neptune, the Kuiper Belt. This is the home of Pluto and countless other icy dwarf planets. For decades, we thought of these worlds as little more than inert, frozen snowballs. But the flyby of Pluto by the New Horizons spacecraft in 2015 blew that idea completely out of the water. It revealed a world that was stunningly, bafflingly active. We saw vast, smooth plains of frozen nitrogen, like the famous heart-shaped glacier informally named Sputnik Planitia. This plain is almost completely free of craters, which means its surface is incredibly young, constantly being renewed. Scientists believe this vast sheet of nitrogen ice is slowly churning and convecting like a giant, slow-motion lava lamp. We saw towering mountains, several kilometers high, made not of rock, but of water ice, which is as hard as granite at these temperatures. We even saw what looked like cryovolcanoes that may have erupted a slushy mixture of water, nitrogen, and ammonia onto the surface.
All of this geological activity requires energy, but Pluto is so far from the Sun that sunlight provides almost no warmth, and it has no giant planet nearby to stretch it with tides. So where does the heat come from? It must be coming from within. It's thought that the slow decay of radioactive elements in Pluto's rocky core is generating just enough residual heat to keep its interior surprisingly warm. And here is the most exciting implication. This internal heat may be enough to maintain a vast liquid water ocean deep beneath its surface, trapped and insulated by the thick outer shell of water ice and frozen nitrogen. The idea that a small distant world like Pluto could have a hidden ocean was a revelation. And if Pluto can have one, then it's likely that many other large Kuiper Belt objects, worlds like Eris, Makemake, and Sedna, could also have them. This has led to a paradigm shift in astrobiology. The number of potential ocean worlds in our own solar system might not be just 2 or 3, but dozens. The cold, dark, outer reaches of the solar system might be filled with hidden, potentially habitable environments. Our final long-shot candidate is Neptune's largest moon, Triton. As we mentioned before, Triton is a strange one. Its retrograde orbit tells us it's a captured object, likely a dwarf planet from the Kuiper Belt, much like Pluto, that wandered too close to Neptune and got caught in its gravity. When Voyager 2 flew by in 1989, long before we saw Pluto up close, it gave us a sneak peek at what these worlds are like. And it saw a dynamic, active surface with geysers of nitrogen gas erupting from its icy crust. For the same reasons as Pluto, it's now thought that Triton too could harbor a hidden ocean, kept liquid by the heat of its capture and the radioactive decay in its core. And so our tour of the potential gardens of our solar system comes to a close. We've seen the ghost of a habitable past on Mars. We've explored the tantalizing hidden oceans of Europa and Enceladus. We've pondered the strange alien seas of Titan, and we've considered the surprising potential of worlds from the clouds of Venus to the distant icy dwarf planets. The conclusion is inescapable. The raw ingredients for life, water, energy, and organic chemistry, are not rare and special. They are common, perhaps even abundant, throughout our solar system. This leads us, as we settle into the quiet of the night, to a very profound and very gentle question. A question that was famously posed by the physicist Enrico Fermi while having lunch with his colleagues in 1950. It's a question that has haunted scientists and dreamers ever since. If the ingredients for life are so common, and the potential homes for that life are so numerous, even just within our own solar system, then where is everybody? This is the heart of the Fermi paradox. It's the strange, quiet contradiction between the high probability that life should be common in the universe and the complete and utter lack of any evidence for it. The sky, for all its beauty and wonder, seems to be silent. There are no radio signals from other civilizations,
No signs of alien engineering, just us. Why? The paradox admits many possible answers, some hopeful, some unsettling, but all of them deeply thought-provoking. And exploring them is a perfect way to contemplate our own place in the cosmos as we drift off to sleep.
One set of answers to the paradox suggests that maybe we're just not looking correctly, or we haven't been looking long enough. The universe is incredibly old, and a civilization might only be loud and detectable for a short period of its history. Maybe they have moved on to forms of communication we can't possibly understand. Or maybe they are deliberately staying quiet, hiding from something we don't yet see. Or perhaps the distances are just too vast, and we are simply too far away to have heard from anyone yet. These are the more optimistic possibilities. But there is another, more sobering line of thought, known as the Great Filter Theory. This idea suggests that there might be some kind of universal roadblock, a filter that is incredibly difficult for life to overcome. There may be a step in the evolution of life that is so improbable that almost no planet ever gets past it. We don't know what that filter might be. Perhaps the filter is right at the very beginning. Maybe the leap from non-living chemistry to the first simple, self-replicating cell is so extraordinarily rare that it has only happened once here on Earth. Maybe the ingredients are everywhere, but the spark of life itself is a near impossibility. Or perhaps the filter lies later on. Maybe simple microbial life is actually very common throughout the universe, but the leap from a simple prokaryotic cell like bacteria to a complex eukaryotic cell, the kind that makes up all plants and animals, is the great filter. This was a transition that, on Earth, took over 1 billion years to happen, and it might have been a 1 in a trillion fluke. If this is the case, the universe might be teeming with microbial slime, but almost completely devoid of complex animals. Another possible filter is the development of intelligence itself. Complex life might be common, but maybe intelligence, the kind that can build telescopes and wonder about the universe, is an incredibly rare evolutionary trait that doesn't have much survival value in the long run. Or perhaps the filter is still ahead of us. Maybe all intelligent civilizations eventually develop the technology to destroy themselves through nuclear war or environmental collapse before they ever get a chance to colonize the stars. It's a humbling and cautionary thought. In this scenario, the silence of the sky is a warning. This leads us to a related idea, a concept known as the rare Earth hypothesis. This hypothesis suggests that while the ingredients for simple life might be common, the conditions needed for complex life, like us, are so incredibly specific and numerous that the Earth might be a very, very special case. It's the idea that our planet won a long series of cosmic lotteries. Let's think about some of them. First, there's our star, the Sun. It's a relatively stable, long-lived star. It's not a hot, blue giant that might burn out too quickly for complex life to evolve, nor is it a small, volatile red dwarf that might blast its planets with frequent sterilizing flares.
It's in a calm, quiet, Goldilocks-like period of its life. Then there's our position in the galaxy. We live in a quiet, suburban spiral arm, far from the dangerous, radiation-filled core of the Milky Way, and far from the dense globular clusters where nearby stars could go supernova and sterilize our planet. We have a relatively peaceful orbit.
So we have all the ingredients from our recipe. We have liquid water, and a lot of it. We have energy, not from the sun, but from the constant tidal flexing of Jupiter's gravity. And we almost certainly have the right chemical building blocks, delivered by comets and asteroids over billions of years, and likely leaching from the moon's rocky core into the water. The question then becomes, what might be happening at the bottom of that ocean? On Earth, deep beneath the waves where no sunlight can reach, we have hydrothermal vents. These are cracks in the seafloor where superheated, mineral-rich water from the planet's interior gushes out, creating a kind of underwater hot spring. And these vents are oases of life. They support entire ecosystems of strange and wonderful creatures that thrive in total darkness, powered by chemical energy. It is a very real possibility that Europa's ocean floor is home to similar hydrothermal vents. If so, they would be the perfect environment for life to arise and potentially to thrive. Imagine, deep beneath kilometers of solid ice, in an ocean that has not seen the sun for billions of years, a chain of these warm, chemical-rich vents. It's one of a handful of places in the solar system where life could plausibly exist right now. Of course, getting there to find out is an immense technological challenge. Future missions, like NASA's Europa Clipper, will perform dozens of close flybys to map the ice shell, confirm the ocean's depth and salinity, and even try to sample the faint plumes of water that may be erupting from the surface. An even more ambitious future mission might send a lander, and perhaps one day a cryobot, a robotic probe that would melt its way through the entire ice shell to finally dip its sensors into that hidden alien sea.
And so we are left with these profound, quiet questions. Are we alone? Are we the first? Or are we just one of many, separated by an ocean of space and time so vast we cannot yet hear each other's voices? The search for life in our own solar system is the very first step in trying to answer that question. It's our way of testing the recipe. If we were to find even simple microbial life on Mars or Europa or Enceladus, it would be the single most profound discovery in human history. It would tell us that the spark of life is not a miracle unique to our world. It would suggest that the universe is teeming with life and that the stars are not as silent as they seem. But even if we search and find nothing, that discovery too would be profound in its own way. It would tell us just how precious, how rare, and how incredibly lucky our own living world is. It would underscore our responsibility to protect this pale blue dot, the only home we have ever known. The search for life, in the end, tells us as much about ourselves as it does about the universe. It reflects our deepest hopes, our innate curiosity, and our desire to find our place in the grand cosmic story. Whether we are alone or part of a vast cosmic biology, the quiet,
patient act of looking is one of the most noble and meaningful things we can do. So as you drift off, let your mind ponder these possibilities. Let the quiet mystery of it all be a soothing presence, a gentle reminder of the vast and wonderful universe you are a part of. Sweet dreams.